Okay, the next talk is a recorded talk, so you can read the title and the authors. I think Meg-Yuan Zhang is giving the talk, or, well, I don't know, in fact. Sorry about that. So we can start.
Hello everyone, I'm Mengyuan Zhang, a PhD from the Institute of Software, Chinese Academy of Sciences. Today I will tell you about our research titled Quantum and CPA Security Notions for AEAD. Okay, let's first start with a quick overview of this presentation. First, I will review the classical and CPA notions and how it can extend to the quantum settings. Then I will discuss whether these quantum notions apply to AEAD. And this is a key question of our work. And what makes this work a bit different from previous work is that I will put more emphasis on the quantum circuit perspective, and I will talk more about why later. So let's get started. To begin, let's first briefly review the classical and CPA security notion. This notion measures the privacy of an encryption scheme by evaluating the adversary's advantages in distinguishing two encrypted messages. To formalize this, we define the following security gain between an adversary A and a challenger C. So the notion consists of two phases, the learning phase and the challenge phase. In the learning phase, the adversary is querying the encryption oracle, and in the challenge phase, the challenger first picks a random bit B, which is either 0 or 1, and the challenger responds to its challenge queries depending on this random bit B. And the adversary's goal here is to guess this bit B. We call the way that the challenger responds to its challenge query is return type. And there are three return types in the classical setting: one ciphertext, two ciphertext, and real random. In one ciphertext, the adversary submits two equal-length messages M0 and M1 and receives back the encryption of MB for the challenge bit B, while in the two ciphertext, the challenger retains both the encryption of M0 and M1, but the order returned depends on its bit B. And third way of implementing a challenge query is real random, that is, the adversary sends one message M, and it receives back either the encryption of M or encryption of a random message. In the classical setting, these three IND notions are proven to be equivalent. So to analyze the quantum security of encryption schemes, we need to extend the classical IND security notions to the quantum setting. A key aspect of this extension is defining the capability of a quantum adversary, specifically how it can query the encryption oracle using quantum superpositions. And the natural approach is to allow the adversary to make quantum queries in both the learning phase and the challenge phase. The first formal quantum IND notion was introduced by Bonnet and Gentry, known as FQ and QCPA, or fully quantum IND and quantum CPA notion. They consider the following settings. That is, the adversary is allowed to make standard quantum queries to the encryption oracle in both the learning phase and the challenge phase, where the standard quantum query is modeled as an oracle that maps XY to XY, XOR FX. And the return type of the challenge ciphertext is one ciphertext. However, Bonnet and Gentry found that this notion is unachievable. That is, no encryption scheme can satisfy this security notion. Then, to address this issue, they proposed a relaxed notion called IND-QCPA. In IND-QCPA, the adversary is allowed to make quantum queries only during the learning phase, while the challenge phase is restricted to classical queries. After Bonnet and Gentry's work, many studies have focused on formulating IND-CPA security in the quantum setting. The key idea is to define achievable quantum IND-CPA notions by combining different quantum query models with various return types. A query model essentially describes how the adversary interacts with the encryption oracle. Previously, I introduced the standard query model, which remains the basis for most quantum attacks today. But beyond this, two other models have been proposed: the embedding query model and the erasing query model. Well, the main difference between the embedding query model and the standard query model lies in how the output register, that is Qout, is initialized. Where standard query model allows the adversary can initialize the output register to any quantum state ycat, while the embedding query model fixes the initial state of the output register to 0cat. The erasing model, also known as the minimal query model in other works, it operates in an in-place manner, that is, the input and output share the same register. It directly maps X to Fx. Carstens et al. Conducts the most comprehensive study so far on quantum CPA notions and the relationships between them. Specifically, they consider combinations of the following three options: the query model, return type, and the number of queries. For the query model, the adversary is allowed to make classical query, standard query, embedding query, or erasing query to the challenger. For the return type, it follows the classical setting, that is, including one ciphertext, two ciphertexts, or a random. And the number of queries could be 0 or 1 or many. Now, based on their framework, we want to ask the following two questions. The first question is that their result and proofs hold for general encryption schemes. So, when the subject of study is AEAD, that is, authenticated encryption with associated data, are these quantum CPA notions still applicable? And the second question is that the implementation complexity of the erasing query model is controversial. At the beginning of this presentation, I mentioned that I would focus more on the quantum circuit perspective, so why talk about implementation efficiency? First, as shown in the first work of Carstens et al., there is a hierarchical relationship between security models. For example, there exists security notion A and B such that A implies B, but B doesn't imply A, where A and B may be based on different query models. This means that quantum security of a scheme is inherently tied to its query model. The second point is that the query model is a direct abstraction of how the scheme is implemented as a quantum circuit. So, in the post-quantum area, if an encryption scheme is never going to be implemented, for example, as an erasing type circuit, then what's the point of evaluating its security under the erasing query model? The erasing query model actually corresponding to an in-place implementation, and only bijective or injective functions can be realized in this form. Let's first consider a case where F is bijective, which naturally leads us to block ciphers in the context of cryptography. First, for AES and more generally SPN-based ciphers, in-place implementation are not as straightforward, but recent works, including the two referenced here, have successfully built in-place implementations and achieving better efficiency in certain aspects. While Fisto-style block ciphers can be naturally implemented in-place by leveraging a standard oracle for the underlying function f, big F, as known in the right figure. However, the case where f is injective function is more challenging. Here we present the implementation method given by Carstens et al. for function f from n-bit input to n-bit output with n less than m, first we need to construct a bijective function f hat such that for any n-bit string x, it satisfies the following relationships. That is, f hat has only 2 to the power of n point determined by function f, and the function values at the remaining points can be chosen arbitrarily. Second, we have to implement the corresponding unitary operator for f hat. Finally, we have to implement the erasing oracle for f in the following way, which involves first applying the embedding oracle of f hat, swapping the input and output register, and applying the standard oracle of the inverse of f hat. Then we have that the overall complexity is at least 2 to the power of f minus 2 to the power of n. Then such high complexity leads us to ask the following question, that is, in the post-quantum area, will an injective function be implemented as a quantum circuit in the form of an erasing oracle? Our answer to this question is yes. We will provide specific examples later, where at least some authenticated encryption schemes, which are injective functions of plaintext input, but can be efficiently implemented as an erasing oracle. Then, as long as such schemes exist, it makes sense to study the security of algorithms in this current model. In this work, we focus on AEAD, that is, authenticated encryption with associated data. An AEAD scheme consisting of an encryption function and a decryption function, where encryption function takes nonce n associated data A and plaintext M as input, compute a ciphertext C and a tag T, and return the tuple NaCNT. Decryption function takes NaCNT and returns the decrypted plaintext M if the authentication check is successful. Otherwise, it returns an error symbol. The standard query model and the embedding query model can be naturally extended to the AEAD setting. Here, we consider the associated data and the message may be in quantum superposition, while the nonce remain in a classical value and is therefore not represented in this figure. Standard oracle takes AMY as input and output AMY XOR CT. And embedding oracle takes AM as input and output AM and CT. However, as I mentioned earlier, only injective and bijective functions can be implemented as erasing type circuit. For AEAD schemes, since the associated data is only authenticated but not encrypted, it clearly doesn't meet this condition. But interestingly, we found that AEAD can still be implemented in the following form as an oracle. We call this query model the ERAE query model. And the ERAE query model maps AM to ACT. This model is reasonable since, first, from a functionality perspective, we need to return the entire associated data register to support decryption and verification on the receiver's side. Second, from a theoretical perspective, the encryption algorithm is essentially injective for fixed A and N. In other words, it satisfies the following function relationship and acts as a one-to-one mapping with respect to M, with respect to message input M. Finally, from a circuit level perspective, we also constructed an example to demonstrate this. This is a simplified ERAE type quantum circuit of OCP3 where the XOR offset operation has been omitted. And this is the algorithm of OCB3. To implement OCB3 as an ERA type circuit, we need to implement all block cipher used for associated data processing as standard oracles, all block ciphers used for message blocks processing as erasing oracles, and the block cipher used for XOR sum of the ciphertext blocks should also be implemented as standard oracle. And there, where I denotes this is the input register of this oracle, O denotes this is the output register of this oracle. As a result, the overall output of the circuit will be A, C, and T, and this ERA type circuit. So now we can theoretically calculate all possible quantum and CPA security notions. First, the query model, which can be classical, standard, embedding, or ERAE. The return type, which including one ciphertext, two ciphertexts, or real random. And we consider the number of queries in the learning phase could be 0 or many. The number of queries in the challenge phase could be 1 or many. So for the learning queries, we have 1 plus 4, 5 choices, where 1 corresponding to the case no learning query. And for the challenge queries, we have 4 times 3 times 2 choices. Then we get 120 possible notions. We exclude some notions. So excluded notions are the notions that have different quantum queries in the learning phase and the challenge phase. For example, the learning queries are standard queries, while the challenge queries are embedding queries. There are 36 notions of this category. In addition, there are some notions that correspond to the one-time CPA notion. That is, there is only one challenge query and no learning query. There are 12 notions of this category. Also, some of the notions are impossible to achieve by any AEAD scheme, and there are 20 impossible notions. So after filtering this out, we are left with 52 security notions. Notably, when the challenge query module is ERAE and the challenge ciphertext return type is real random, we make appropriate adjustment to the real random return type, primarily due to their incompatibility. Let's first recall that the definition of classical real random, the adversary submits a message M and either gets its encryption or the encryption of a random message. Now, when extending this to the quantum setting, we can't use the same definition directly, as the message M may be in superposition. So the common approach is to define quantum real random using a random permutation pi and applying pi to the adversary's root query if bit B is 1. Then the following issue arises. Supposing the adversary submits this quantum state as a challenge query, where A is a single quantum state and M is in superposition. Then when bit B is 0, we just send this query through the ERA oracle, so the A register remains unchanged. But when bit B is 1, the challenger has to first apply a random permutation pi to A and M before passing it through the ERA oracle, and this will induce an entanglement between these two registers. Then the adversary can measure this register and immediately detect that it has changed. Moreover, we are unable to restore a register since the message register has already changed. So in response to this situation, we proposed a compromise solution, that is, adjust the real random to the tiled real random return type. Preciously, this approach considers the associated data input and message as two independent interfaces. And instead of picking one random permutation pi and applying it to A and M, the tiled real random return type assumes the challenger picks two random permutations, pi A and pi M, and separately apply them to A and M. In the classical setting, these two return types are indistinguishable, and this has been proven in our paper. Moreover, the security notions based on the tiled real random return type are still strong, and this can be seen from our final result. And this is a table of our result. Our paper proves the implications and separations between different security notions. Some of these implications allow us to group equivalent notions together, and this resulting to 12 panels. However, the table labels the panels as P1 to P14, skipping P4 and P8 to align with the results with Carstens et al. This table presents the implications and separations between certain panels, while the seal marked with a question mark indicates open problems. We can see from the table that P1 and P2 collectively imply all other security notions, but there is a separation between P1 and P2. And the security notions in panel 1 are all based on ERA query model, and the security notions in panel 2 are all based on standard query model. This means that when evaluating the security of an AEAD scheme, or as a designer, one could design an encryption scheme that is probably secure under both P1 and P2, or, for example, only guarantee its security under P1, and then provide recommendations for implementing the encryption scheme as an ERA type circuit. And our results also reveal the relationship between the quantum circuit of encryption primitives and their post-quantum security. And there is a figure of their relationships. Thank you for listening.
Okay, as for the previous recorded talk, there is no possibility for questions, so please address the question to the author by email. Now we are done